Science Lab, and today I'm looking at an interesting GRE math subject test problem that I got incorrect when taking the actual test. So it's a set theory problem, which happens to be number 16. So suppose that x and y are sets f mapping x to y is a function, a and b are subsets of x, and C is a subset of B. Which of the following must be true? 1, f of A union B is equal to f of A union f of B. 2, f of A intersect B is equal to f of A intersect f of B. And 3, f of C is a subset of f of B. So let's examine each claim. Now, when you're doing equality proofs, that means you have to do the necessary side, proving that if something is in A, it is in B, and then the sufficient side, proving that if something is in B, it is also in A, which means that the two are practically equivalent. If you can only do one side, all you're showing is that A is a subset of B. But if A is a subset of B, and B is also a subset of A, that automatically means A is equal to B. So let's try it with these. Claim number 1, if f of A union B is equal to f of A union f of B. So first we have to start by doing the necessary proof. So that means if x is in f of A union B, actually x is probably confusing to use given there's also a set named x, so let's call it n. If n is in f of A union B, then let's show that it's in f of A union f of B. So if this is true, what do we know? We know that f inverse of n, if it exists, or whatever mapped, so f minus 1 may not exist over the entire domain, but we do know that, of course, given that n is in this set right here, there must exist some, m in A union B such that f of m is equal to n. So then, we know that m is in A union B, right? So then that means that m is automatically in A, and it's, m is, correct, sorry. So that means that either m is in A or m is in B. If m is in A, then we can say that f of m is in f of A, which means that n is in f of A. Or maybe m is in B. It could be in both too, but then it's just covered by either one. Then f of m is in f of B. So then n is in f of B. So it could either be in f of A or in f of B, which means that it's guaranteed to be in their union. Remember, we're only 25% of the way through this proof. Now for the sufficient side. N is in f of A union f of B, so n is in f of A union B. So what do we have to do? Well, now we know n is in f of A or n is in f of B. So, like I said, there has to exist some m in either one of these slots. Okay, so if n is in f of a, there must exist some m in a, such that, well, of course, f of m is equal to n. And if this is true, there must exist an m in b, such that f of m is equal to n. Which means that whatever maps to n has to be in either a or b, and thus it must be in a and b. Which means that f of m has to, of course, be in f of a and b. There we go. All right. So we just showed that 1 is true. And you might think this is trivial, right? Aren't all three of them true? But you're about to hit a really cool plot twist. So let's attempt 2. F of a intersect b is equal to f of a intersect f of b. Now, when I was actually doing this during the timed practice GRE, I opted to do only the necessary proof, but not the sufficient one. So, if n is in f of a intersect b, that means that whatever maps to n, let's say m, is in a intersect b. All right. So then that means that m is in a and m is in b for sure, because it's in their intersection. Which means that f of m, which is n, must be in f of a, and n must be in f of b as well. So, of course, has to be in their intersection. And I left it there thinking that that would be the right answer. But you also have to go through the sufficient proof. All right, so then assume n is in f of a intersect f of b. Then we know that n is in f of a and n is in f of b. But what does that exactly mean? That means there exists some m in a such that f of m is n, and that means there exists some j in b such that f of j is equal to n. Remember, it didn't say f was a bijective function. So that doesn't mean it has to be one-to-one, such that every single input can only have, every single output can only have one input corresponding to it. We don't know that just from what we're given. So then we have that m and j could be two completely different elements, which means that we can't exactly say that n is in a intersect b. Why? Because m could be in a and m could decide to not be in b, and same thing with j. J could be in b and decide to not be in a, which means neither of them are in a intersect b, which means that f of m and j is not in f of a intersect b. There is a possibility that this is not true because we don't know this is a one-to-one correspondence, which means that 2 is false. Bam, there's the big plot twist. And finally, we get through 3. Well, we already know 1 is true, and we already know 2 is not true, which means that this is covered up, this is covered up, and this is covered up, which means the obvious answer is D, but let's still get through 3 regardless. All right, so how do we know exactly that this has to be true? Well, I mean, it's pretty obvious. If n is in f of c, that means there exists an m in c such that f of m is equal to n. And so that means that if m is in c and c is a subset of b, that means m is also in b, which means that f of m is also in f of b, which means that n is in f of b. And we don't have to do it the other way around because we're only proving that f of c is a subset. In fact, if we did it the other way around, it would show us that it would be incorrect. So that means 1 and 3 are both true, which means the answer is D, 1 and 3 only. That's it. Thank you everybody for watching.